So today we're going to start talking about the web as a client-server system and the architecture that underlies SaaS applications, because the architectural choices that we make are actually common to any SaaS application. They predate a lot of the material that is specific to Ruby and Rails. So one of the key lessons that we're going to talk about through the rest of this segment is that whenever you do an architecture, you're making some choices about the way that components fit together in that architecture. And we're making some choices around the fact that our architecture is software as a service, that we're using open standards. So in cases where we're making a choice, we'll also illuminate what some other possible choices might be. So in terms of this diagram that's reproduced from the book, we're going to start at this top level right up here, where in the simplest possible manner, we think of a web browser, we think of a series of tubes in between, and we think of a site where you want to end up and get some content. So from 100,000 feet away, using height as an analogy, and as we sort of go closer to the ground, we'll see more detail, you can think of the web as a client-server architecture, which means that it's request and reply oriented. A client is a thing that asks questions. A server is a thing that gives answers. And fundamentally, each piece of software, the client and the server, is specialized in some way for that role. Now, in our case, the client is a web browser like Chrome or Firefox or Safari or Internet Explorer. The website or the web server is the server part. And in between, we have the internet, which kind of magically routes content from one end to the other, which we're not going to go into a huge amount of detail about, but we will give you the basics. So the simplest possible interaction, the web browser asks a server for something. That's the client asking a question of the server. The server responds, the response comes back. How does this all happen? Well, there's a long history of a set of protocols going back to the 60s called TCP/IP, for Transmission Control Protocol and Internet Protocol. And starting with the second half of that, here's the sort of one-slide crash course on what you need to know. The Internet Protocol is a set of rules that computers agree to follow in order that they can all interoperably talk to each other. And you probably have seen these Internet Protocol addresses, IP addresses. There are 4 integers separated by dots. They're often called 4 octets because each integer can be an 8-bit number. There's a special address, 127.0.0.1, which always means this computer, whichever computer I'm running on right now, as opposed to being a unique address of some machine somewhere else. So in general, every machine in the universe has more or less a unique address, although with routers and network address translation, that's a little more complicated than it once was. There's also a special name called localhost that in the Unix world and on any computers that sort of derive their ancestry from Unix, the name localhost means this machine that I'm running on right now. And we're going to use this fact in doing a simple example in a moment to show how the internet works. Now, IP just says if you give me the address of a remote machine and a small bit of information, a packet, which is really only a few hundred bytes of information, I will do my best to get it over to that other machine, but there's no guarantee that it'll get there. And furthermore, if you send multiple packets, for example, you've got too much information, you've got to break it up, there's no guarantee that they'll arrive in order, or that some of them will arrive at all, or that they will arrive completely free from errors. So on top of IP, there's an additional layer of protocol called Transmission Control Protocol, or TCP, whose job it is to make sure that all of the right things happen. TCP essentially monitors the IP packets and makes sure that if there's a gap in the order in which they're delivered, that it re-requests the packets that got lost. If there are errors in transmitting the packets, it re-requests the corrupted packets to make sure that it gets them all correctly, and it reassembles them in the proper order. The result being that as a programmer, you can have the luxury of the illusion that you're sort of putting long strings of characters or bytes into a pipe, and at the other end, they're coming out of the pipe in the same order, reliably, and you can just think of it as printing strings, pretty much. Now, one nuance is if we want to have multiple different programs on the same computer all using TCP, we need a way to identify which traffic streams are intended for which programs, and the way TCP does that is by using port numbers. A port number is just a 16-bit number that it essentially identifies a particular program running on a certain machine and says this traffic is intended for that program to consume. And as we'll see, in the case of the World Wide Web, it's been decided by the powers that be that port number 80 is the standard port on which web servers should listen for traffic. So in a moment, we're going to do a very simple demonstration of running our own very brain-dead web server, just so you can see how simple the protocols really are. Of course, any protocol effort like this is a result of decades of work by a lot of people. But I think the 2 gentlemen who are given credit for really making these ideas real and putting them into practice as TCP/IP are Vint Cerf and Bob Kahn, who shared the Turing Award in 2004 for their work on network protocols, which ultimately led to the development of TCP/IP, which now powers billions of computers all over the world. So how does this work? The beauty of TCP/IP is I can pretend that I've got a pipe into which I'm going to put a string, like get/bears, At the other end of that pipe, there's somebody listening who is able to pull out that same string just how I put it in. The other side will come up with some reply to my question. For example, here's a line that says, everything is fine and the content is coming your way. And they send that response back to me and I pull it out. So it really gives you the illusion of a reliable sequence of bytes that can go in either direction. So it's a bidirectional or full duplex protocol. Now, I lied when I said that at the simplest possible level, there's just a client and a server. In fact, there's a third piece of the web that's very fundamental to how it works, which is DNS, Domain Name System. And that's the service that allows us to use meaningful names like google.com or microsoft.com instead of trying to remember those addresses with 4 numbers separated by periods. The domain name server is actually a separate kind of service, so the diagram I showed before really should have looked like this. When I want to talk to a web server, really the first thing I do is I have to go look up the Internet Protocol or IP address of that server from a DNS server, and DNS servers are usually configured by whoever your ISP is. Once I get that information back, now I have the IP address and I can do what I really want it to do. So the irony here is that even though DNS is a totally separate service, for all practical purposes, most of us would think the internet was down if DNS wasn't working, because most web browsers and other programs no longer rely on being able to just remember the raw IP addresses. They rely on being able to do this mapping at runtime. So now that we know how to talk over TCP/IP, what do we say? The way that we exchange content between browsers and web servers is a very, very simple network protocol called Hypertext Transfer Protocol, or HTTP. It is ASCII-based. That means that everything that goes back and forth asking for stuff and getting the status of whether that stuff can be returned or not, those are just plain old strings. They're easy to read. Human beings can decipher the protocol. An HTTP request is very simple. There's a request method. Get and post are the most common ones, but there's 3 or 4 others that you'll come to meet during the rest of the course. There's a URI. You've seen these before. The URI names the thing that you would like to retrieve. And the HTTP protocol version, a very important lesson from the networking literature, is when you deploy a protocol that many millions of clients and servers are going to use, one thing you should put in the protocol itself is for each party, when it speaks, to identify what version of the protocol it's using. And the reason to do this is that if you upgrade the protocol or add features in the future, you want to make sure that if somebody asks you for something using an old version of the protocol, you don't accidentally use these new features that the older clients maybe haven't been upgraded yet. There's also some protocol headers in HTTP. They give some extra information, both for the client's point of view and from the server's point of view, that accompany the request or that accompany the reply. And the most important HTTP requests and replies that we'll see is we'll get a status code back from the server of all is well, the resource has moved, like a redirect, or there was some kind of a problem and I wasn't able to serve your request. Now, this is all much easier to see in demonstration form than it is to do on a slide, so let's do a very simple demo. What I've got is I've got an instance of a Google Chrome browser here, and I've got a terminal window where I'm going to run a program that is a standard part of Unix called netcat, NC. And I'm going to say listen on port 8000. Remember I said TCP uses port numbers to identify different programs that want to receive TCP traffic. So I am now a program that is waiting for somebody to send me some traffic on port 8000. We're going to go over to our web browser and create that traffic. Remember I said localhost is the magic name that means this machine that I'm running on right now. I'll make sure that we're using HTTP. And you can follow the host name with a colon and a port number. Remember I said that port 80 is the default port for web traffic. So if I didn't include a port number in the URI, 80 would be assumed. But in this case, I want to make sure that I direct some traffic specifically to this terminal window that we're listening on. So let's see what happens if we try to visit this URL. And you can see that the web browser has sent over a request. It's saying, I want to get the root resource because I didn't put anything after a slash or anything after the hostname part of the URI. It's identifying the version of the protocol that it knows. I know protocol version 1.1. So that means that the server is, in its best judgment, it's going to reply and only use features of the protocol available in 1.1 and earlier so as not to confuse the client. The client gives us some more information about itself, like what kind of a computer I am. I can see that I'm running a Mozilla-like browser on a Macintosh and so forth. And now you can see our web browser is just sitting here. We've got the little spinny circle that indicates the browser is waiting for something to happen. And that's because it's waiting for a reply. So we're going to give it the simplest possible reply. And sure enough, there's hello world. Now you notice that before anything appeared, I had to essentially quit out of the netcat program and close the connection, because that's the easiest way to tell the browser, I've finished saying everything I'm going to say. And at that point, the browser pulls the string of characters out of the TCP pipe and displays it. Now we broke a few rules here. Technically, what we should have done is we should have included some headers like this, telling the browser what's coming your way. In our case, we were just going to deliver some plain text, and for historical reasons, browsers are very tolerant if you just return some plain text without any other identifying information. They tend to do the right thing. But the big message here is you've just seen, in its simplest form, what HTTP does. The client asked a question, there was a server on the other end waiting for questions to be asked, and we supplied an answer to that question, which then went back to the client, back to the web browser. Now, one issue that we haven't talked about yet is early on in the design of HTTP, a decision was made that the protocol would be stateless, which specifically means that whenever I make a new HTTP request to any particular server, it's as if that server has never seen me before in its life. So the corollary of that, if there's any information that has to be maintained across requests, then there has to be some separate mechanism for doing that. And an easy example of this is even in early web apps, there's a notion of going through a flow of pages in the application. For example, you visit a product page, you add something to your shopping cart, you check out, and somehow the server has to remember which step you're on. So how can it do that if every request from you is independent and it's as if every request was like the first time? Cookies were invented to do this, and essentially the first time that you visit a site, the site has the option of sending back, along with its response, a little piece of information called a cookie, and most of the time, that's really just a name for some state that the server is going to maintain about you. The web browser's job is to remember that cookie, and anytime you make another visit back to that same server, make sure that that cookie value is supplied along with it. So cookies essentially provide a way of saying, hey, remember who I am? You served me this cookie value, and now you can look me up. You can remember what I was doing last in your application. And as you might expect, as a framework that's mature for doing SaaS applications, Rails has pretty good facilities for handling cookies so that you more or less don't have to worry about it.